All right, guys. Hey, in this video, we're going to be going over question number 2 of the free response questions that were released by College Board yesterday. This is going over the May 6th, 2025 AP Chemistry exam. And again, if you're watching this on YouTube and you're not one of the students at West Springfield, then you've already taken the test probably. But our students at West Springfield haven't taken the test yet, and we're using this as some extra review to gear up for the test date that we're taking it on May 21st. And then also, if I refer to units, I'm not referring to College Board's AP Chemistry units. I'm referring to West Springfield's AP Chemistry units, and they're not the same. So if I say Unit 1, that might mean something different than Unit 1 from College Board, okay? So question 2 kind of starts off with a combustion analysis. Then we go into acid-base titration, a little bit of buffer knowledge. Then it goes into kinetics. Then it goes into intermolecular forces, atomic molecular structure, and then thermodynamics. So, question 2 is all over the place in terms of like what it's covering, like unit by unit by unit. And that's usually how they go, but this one's kind of very sporadic. At least I thought when I was going through it, okay? So question 1, they give us, we have a compound made of carbon, hydrogen, and oxygen. It's absorbic acid, and we probably don't know the formula for absorbic acid or the empirical formula for the absorbic acid off the top of our head, so we got to use the information given. So we completely combust this compound, we get this much CO2, we get this much water, and we want to use that information to figure out the empirical formula, essentially. So the first thing is just calculate the moles of H2. So we would just take the grams, or sorry, H2O. We would take the grams of H2O divided by the molar mass of H2O, and we get, if we round to 4 sig digs, which were allowed here, we get 0.1600, okay? So that's how many moles of H2O we have, okay? Then they tell us that the carbon and oxygen ratio in the formula is 1:1. So whatever the subscript is of carbon, that's going to be the subscript of oxygen. So that's nice and friendly for us. And then, so basically we just have to figure out what the subscript of hydrogen is, okay? And so the way, I like to do it is, we have C 0.24 because we had 0.24 moles of carbon, right? And we know we had 0.24 moles of carbon because we had 0.24 moles of carbon dioxide produced, and all the carbon in the carbon dioxide came from the burning of this compound, so it came from this compound. And the subscript of carbon is 1 in CO2, so moles of CO2 equal moles of carbon, and all those moles came from here, right? So I know my subscript for carbon is 0.2, I know my subscript for oxygen is, 0.24, my subscript for oxygen is 0.24, and then where did I get this 0.32, the subscript for hydrogen? Now, we figured out moles of H2O, and what we'd have to recognize is that if we take the moles of H2O and we double it, that would give us moles of H, right? Because there's 2 H's and 1 H2O. All right, I'm thinking this might be one of the 2 pointers from question 2. 1 point for knowing to double the moles of water to get moles of hydrogen. I don't know, that's just a guess, okay? So remember, once we have our subscripts, we divide by the lowest one, and then we make whole. So when we divide by the lowest one, carbon and oxygen are 1, but hydrogen's 1 1/3, 1.333 repeating. So if we triple everything, we'll get rid of that decimal, so we get C3H4O3, okay, as the empirical formula. Then we get an acid-base neutralization. They give us the volume of the acid. Notice it's monoprotic. You just have 1 H, okay? And sodium hydroxide only has 1 hydroxide, so it's a 1:1 ratio. So this is a perfect candidate for MAVA equals MBVB. We have the volume of the acid. We have the molarity of the base. In part 1, we want the molarity of the acid, and so we have to use our titration curve to figure out the volume of the base. And remember, it's the equivalence point. So we go to the equivalence point, the point of inflection on the titration curve, and it's 16 milliliters. So 16 milliliters is our volume of base. So we have volume of acid, we have volume of base, we have molarity of base. All we have to do is solve for the molarity of the acid. Okay, so the molarity of the acid when we plug in everything comes out to be 0.0880 moles per liter, or capital M. Okay. Now, if you wanted to do it stoichiometry way instead of the MAVA equals MBVB, again, we'd have to get that 16 milliliters for the equivalence point, and we would do 0.016 liters times the molarity of sodium hydroxide. Remember, liters times molarity equals moles, times the 1-to-1 ratio with the acid, and then that would give us moles of the acid we had originally in our container, and then we would divide by the volume of the original acid solution that was measured, which was 10 milliliters, so divide by 0.01 liters, and we would get the same answer. Okay. We want to find the approximate pKa of absorbic acid. So remember, if this is the equivalence point, the volume of the equivalence point, divide it by 2, and you get 8, and that's the half equivalence point. And remember, pH equals pKa at the half equivalence point. So at around 8, we're at about 4. So I guessed 4. I've seen some other people where they've estimated 4.1. I bet they allow a range. It is slightly above the line, so 4.1 is better, but I'm just going to roll with 4. I think that's acceptable. It says approximate, okay? So I'm hoping it's acceptable, but if not, then maybe do the same calculations I'm about to show you with 4.1 as the pKa instead of 4, but it's the same idea, okay? So again, I said around 4 because it's the half equivalence point. And then question 3 asks us the ratio of this when the pH is 4.7. So remember, at the half equivalence point, the ratio of this is equal to 1 because it's a buffer system, and we have our equal components of the buffer system, and when that's true, pH equals pKa, right? Using the Henderson-Hasselbalch equation. So we're up here at 4.7, so that means we have more of the conjugate base than we do the weak acid in the system. So this ratio needs to be above 1, but we're just going to use the Henderson-Hasselbalch equation to solve. Now, if you said 4.1 for part 2, then make sure you plug in 4.1 for the pKa part of the Henderson-Hasselbalch. I just estimated it as 4, so that's what I plugged in, okay? So we would say 4.7, so we're in the Henderson-Hasselbalch, and we're, that ratio is in the Henderson-Hasselbalch. That's the ratio. So pH equals pKa plus the log of that ratio that we're solving for. So basically we're just solving for x. So hopefully we remember how to, deal with logarithms. So 4.7 equals 4 plus the log of x. So that means the log of x equals 0.7. If you had said 4.1 for your pKa, then you would have log of x equals 0.6. And then to solve for x, we would just 10 raised to the 0.7, or if you had, again, 0.6, either 10 raised to the 0.7 or 10 raised to the 0.6, and I get a ratio of 5.01, okay? Now, again, yours might be different if you, used the pKa as 4.1, okay? All right, we keep rolling to the next question. So here we got, our reaction, but it's a rate question. It's a rate law question. It's a kinetics question. So they give us the rate law, and we see that both this acid, dihydroabsorbic acid, okay, or no, absorbic acid, is first order based on the rate law, and the I3 minus is also first order based on the rate law. So we want to explain how this data shows that the absorbic acid is first order. So we would look at trials 1 and 3 because that's where we changed the absorbic acid, but we kept the I3 minus constant. And what we'll notice is from trial 1 to trial 3, we doubled the concentration of absorbic acid. And if we did the math here, we would see that the rate also doubled. So if the concentration's doubled and that doubles the rate, that's the characteristic of a first order reactant, okay? So if you want to explain it in words, looking at trials 1 and 3, we doubled the concentration of this, but we kept the concentration of the other one constant, and we found that the rate also doubled. So that's first order. Now, do the math, right? Trial 3 divided by trial 1 for the concentration equal 2. Trial 3 divided by trial 1 in terms of the rate, that also equals 2. So if the change that happened to the concentration is the same thing that happens to the rate, that's first order. If this came out to be 4, but this was 2, then that would be second order, right? So just, reviewing your kinetic stuff, okay? And then here it says this ion is significantly more soluble in water than just pure iodine. And they want us to give an intermolecular force that's happening between this ion and water that doesn't happen between this molecule, I2, in water. And so basically, it's just ion dipole interactions for this thing, and this thing doesn't have ion dipole interactions because it's not an ion. This is a nonpolar molecule, so all it has is London dispersion forces. If this is dissolved in water, the IMF between iodine and water would be dipole-induced dipole interactions, because the water has a permanent dipole, but a nonpolar thing can have induced dipole interactions from something that's polar or something that's charged. So you could say that the iodine has dipole-induced dipole interactions, but basically you had to recognize that this would have ion dipole interactions. Okay, oops. Okay, so, oh, wait, I skipped over calculating K. My fault. I'll come back to that. So, sorry, part 2, calculate K. Just take the data from one of the trials, plug in the rate, plug in the molarities into the rate equation and solve for K, and then don't forget to get the right units of K. So when you do that, I plugged in trial 1. I get K equals 4.55 times 10 to the negative 4. And the units would be the reaction order. The overall reaction order is 2. So remember, the shortcut is 1 over molarity raised to the reaction order minus 1. So since the reaction order is 2, it would be 1 over molarity to the first power. And it's also always 1 over time for the units of K. And the units of time from the data table was seconds, so it would be 1 over seconds. So you could write it this way. Remember, 1 over molarity is liters over moles, so you could write it liters per mole, or you could write liters times moles to the negative 1 times seconds to the negative 1. Okay, so that would be the correct value of K, and that would be the correct units of K. And then now to part D, we have the ion dipole interactions that we have to talk about that iodine doesn't experience. So ion dipole interactions, the negative charge of the I3 minus will be attracted to the positive dipoles of the polar water molecules. I2 only has LDFs and is not charged, so ion dipole interactions will not occur with that substance I2 that it will with this substance, which is an ion. Okay? All right, so that's question 2 on the FRQ from this year's free response 2025. Hopefully you got all the points, and the next video we'll go over question 3.